A cylinder is inscribed in a right circular cone of height 4 feet and radius equal to 3.5 feet. What is the radius of such a cylinder which has a maximum volume? All right, so you see what we're doing right here. We're sticking a soda can in a cone, right? It's called a cylinder. We're putting it in a cone, and we want it to be as big as possible, maximum volume. What do I mean by that? Well, there's different ways to do it. The cylinder is going to sit on the ground, and it's going to come up until it hits the cone. Think, well, that's just it. Just have it come up. Well, I mean, there's different ways you can make the cylinder. You can make the cylinder really wide, you know, and trying to get more of it. Will that get more volume? Maybe it's not very tall. Again, it's got to come up till it hits. If it's really wide, then it's not going to be very tall because it'll come up and hit the cone, pretty far down. But it'll be wider. Maybe that'll hold more volume. Or you can say, I'm going to make it, come up really high. So it's going to make it narrow, like a tennis ball can, like that. But then that probably doesn't hold much volume because it's so thin. But so no, so if you make it wider, it's like a tuna can, then it's gonna, have some volume. If you make it really narrow, like a tennis ball can, or somewhere in between, like this is kind of in between, where's it, how do you build it and have it come up until it barely fits in there, until it hits the top of the or it hits the sides of the cone, the biggest cylinder you can fit in there. So that's what we want to do. Maximize the volume. Find the biggest sum. So they do this. I mean, this is, a lot of engineering does fitting things inside of each other and making the maximum and things like that. All right. So how do they go about doing that? Well, we already did the setup on another problem. We've got the formula for the volume in terms of R only, not H, right there. So we've already got that. We just need to maximize that volume formula. And so how do we do that? Well, you know how to maximize the volume formula. You take the derivative. So before we take the derivative and set it equal to zero, let's write V. Let's clean that up a little bit. Let's make it nice. So pi r squared. Let's do something with that inside. So we have 4 times 3.5. I'm going to just divide each one separately. By that, see that 3.5, it's the bar, it's under both. So just do it separate. Going to make it easier for doing derivatives and stuff. Then use your calculator. Well, these will cancel out. I'm going to calculate there. Minus. Now, what is 4 over 3.5? I don't know. We go figure it out in Desmos. 4 divided by 3.5. It is, oh, that's too bad. Is there a fraction? It's 8/7. Okay, how about that? Let's go with the fraction 8/7. Or maybe I'll just leave it like it is. I'm just gonna leave it. Who cares? I'm just gonna leave it like it is. It is 8/7, whatever. All right. And now I still haven't done the derivative. Now I'm gonna distribute. Boom, boom. So that'll be 4 pi r squared minus 4 over 3.5 pi r cubed. That makes sense? Because that pi r squared multiply the 4 pi r squared, and the pi r squared multiplied this. So, we got the 4 over 3.5 times pi r squared times r is pi r cubed. All right, now we're ready to take a derivative. Because, that's how we maximize. We want to maximize that volume. So how do we maximize something? We take the derivative of it and set it equal to 0. For now remember, r is my only variable here. Pi is just a number. So we go, okay, bring down that. 8 pi r to the first, right? Subtract 1 from the power minus, bring the 3 down to be 12 over 3.5. And I'll put the pi in the top up there. So pi is over 1, right? R squared, subtract 1 from the power, right? And we're going to set it equal to 0. Because where the derivative is the slope, where the slope is 0, right? If you have a roller coaster at the top and at the bottom, at the max and at the min, at the high and the low points, the derivative is flat. The slope is flat. The derivative is 0. All right, so let's solve that thing. Let's bump this to the other side. So we'll get 8 pi r equals positive 12 pi over 3.5 r squared. Wait, should we do it that way? I mean, we could, but yeah, whatever. Let's just factor out pi r. How about that? Let's just factor. It'll work either way. You can do either way. And this will leave 8 minus 12 over 3.5 R, right? See how that's right? As I multiply that, go back to 8 pi r, multiply that, be 12 pi over 3.5 r squared, r and r, right? Okay, great. So what? Well, that means you can set each part to 0. So this part, pi r, let me do that better. Pi r can be 0, or this part, which is 8 minus 12 over 3.5 r can be 0, right? That's logically, because if two things are multiplying to equal 0, first can be 0, the second can be 0. So let's solve this one. Divided by pi. Boom. So r could be 0 over pi is 0. So you can have a radius of 0. Well, if you have a radius of 0, you got nothing. So that's obviously that's going to be minimum. That's actually the minimum value, and we're not that you, which means you have no volume at all because you have no radius. We're not interested in the minimum. We want to find the max. So bump this to the other side, and we get 8 is positive 12 over 3.5 r, and then multiply by the reciprocal, the upside down, 3.5 over 12 on both sides, 3.5 over 12, because that'll cancel out the 12s, cancel out the 3.5s, and we'll get r equals, and I'm just going to hit the buttons on my calculator. 3.5 over 12 times 8. 3.5 over 12 times 8. So 3.5 over 12 times 8. What do I get? That 2.3333. And so 2.3333. That's the radius. And is that the answer we got? Yep. So that's the radius that will make the biggest soda can fit in. The radius 2.3333. That's we maximized it. This other answer, r equals 0, that was the minimum. You get the smallest can, you get no can. So the best radius, right? Because and the radius could go, remember the radius for the thing, what was it? Oh, the radius was 3.5. So the radius went for the cone went all the way out to 3.5. And we're saying you should make the soda can go out to 2.3333 when the whole thing goes out to the whole cone goes out to 3.5. You should make the soda can go out to 2.33333 and go up, and you'll get the biggest volume soda can you can fit in that cone. So that's fitting one object inside of another. How do they do that in engineering? Maximize, minimize. They use calculus like we just did. There we go.